Hello and welcome to TidyX episode 159. TidyX is a screencast where we go through and explain how our code works. My name's Ellis Hughes.
My name's Patrick Ward. Thanks for checking in at episode 159. I believe we are going to wrap up the package development section that we've been doing,
Series?
series that we've been doing. We've built functions, we built vignettes, we built a package, we did all that stuff.
Documentation.
We're ready to now test the functions and make sure that we go through the checks and balances to ensure that that this function is ready for deployment and things won't break and all hell will go loose. So we're going to wrap that up today. Like and subscribe on the YouTube channel. If there's other stuff you want to see, if there's other series that you want to see us do, some people seem to like the series versus the single episodes. If there's other series you want us to do, like and subscribe, drop the comments down below on YouTube. And as always, we do have a Patreon page. If you feel like the work that we've been doing has been beneficial to you, we are grateful for anything that you'd be willing to contribute back to us. That said, I'm going to kick it over to Ellis. This is way more his wheelhouse on testing and building these things than it is mine, but it is super cool content. So Ellis.
Yeah, I'll be taking us through this and kind of trying to explain why you want to be doing testing and how you can approach doing that. So the whole purpose of testing your code is if you don't have tests in your R package, you're the tester. And what that means is you have to remember for every single function you've written in your package, how they work, the variety of different types of inputs that it could be taking in, and what the correct values should be. On top of that, checking to make sure that it's going to throw the correct errors if somebody puts in the wrong values or values outside of the bounds that you're expecting. And so that's a lot to remember, especially this package here is rather simple. It's only got a handful of functions. It's got its very specific use case. But there are packages that I've worked on that have, tons of different functions inside of them. And it really becomes unwieldy to try to expect to remember exactly how every single function behaves and making sure to test it, as well as making sure if you make any changes to your tests that it continues to behave properly. So we're going to take you through a quick example of tests and show you a variety of different tests that you might use. There's a ton more in the testthat package. So we're only going to cover a handful of them, but these are the ones that I kind of see most commonly. So the way that you'd go about starting adding tests to your R package is using the use this package and the use testthat function. What that's going to do is it's going to add the tests folder. So you can see that right here. It's going to add testthat as a suggest into your description file right there. And then it's going to create this config testthat edition 3 in your description file right there. For the most part, you don't have to be worried about that. Is an R user, just know that that's valuable and useful for you. And that the folks at Posit have already thought a lot about this. But that doesn't actually add any tests to your package. What the next thing you'll need to be doing is using the use test function. Now, if you just use this blank right there, what it'll do is it'll look to see which of your R scripts you have open and create a new test file for you under the tests folder. So you have the test folder, then there's a testthat folder underneath that, and that's where all the content lives. But usually I don't do that. What I actually typically do is I don't necessarily want to be grouping my tests based on the file that they're in. I usually group them by what is the thing that I'd want to be testing. Am I testing errors? Am I testing utils? Am I testing something else? So oftentimes what I do is use the use test, but pass a name into it. And what that's going to do, it's going to create the file, but it's going to be called a test dash and then this string right here. So for example, I'd created an example R script earlier, or run that earlier. So it's use test example, and it created this test-example.r script. So let's open that up real quick so you can see what it looks like. So this is the generic test file that it creates for you. And it's just a very simple test that by default comes included, but it gives you an idea of how tests work in an R package. So first you'll have this test underscore that function that comes from the test that package. And that is a function that allows you to pass a subject and then some code that in theory has some expectations within it. This code is supposed to be able to run independently and not be impacted by any other functions or any other tests that exist inside of your script, which is why they're written in this way, so that it helps you kind of delineate, I am testing this specific thing, right? So kind of read this as test that multiplication works. So kind of read that as a full string. I'm testing that this thing occurs. And so then within the curly braces right here, I can actually zoom in since we're a little zoomed out. Within the curly braces here, we have an expectation. In this situation, it's expect equal, and it's testing that 2 times 2 is equal to the value 4. So what you're saying here is I'm expecting that some situation and then some value is going to be held within that. And what that value is depends on the second piece of this expectation here, and we'll show you a few examples of how that works. But then essentially what it's going to do, it's going to run that code 2 times 2, which we all know is 5. Wait, no, it's 4. And then it's going to check for equality, and then it'll return a true if those two values are the same or false if they're not.
Mhm.
And that's a high level look, but let's go into this package to actually talk you through how you might build it out for your package. Generally speaking, I like to have at least one test for every exported function that I have. So every function I expect my user to interact with, I'm going to have at least one test, if not multiple, testing the variety of different ways they might be adding content into it. And then for any internal functions, if it's an important internal function, I'll probably have a couple tests for it. Again, because it's internal, it's likely that I'll be relying on its behavior, and I want to make sure that its behavior doesn't change unless I intend for it to change. So let's get going on this. So this is our first test within our test-beta.r script. We're testing that get beta parameters works. So it's kind of a high level idea. But we're just going to do a very simple test here. Then within the curly braces, we have the code that we've actually, so we've got these curly braces here, and that's the code that is going to be executed as part of this test. And then at the very, we have this code here, which we become relatively familiar with over this series. We're taking the Laman batting data sets. We're filtering out to keep or remove any individuals that are batted only a handful of times. And we pull out the batting average and get the variance and the average of the batting averages of those individuals and the variance of those individuals' batting averages. So we've done that a whole mess of times over this series, and then we throw it into get beta parameters, and we get this batting av params object, which is a list object. And then we're going to test for two expectations. We're going to expect equal, so we're saying that the value on the left is equivalent to the value on the right, and we're saying that batting average params alpha is identical to 43.48505. And then we're also saying we're expecting equal that batting average params beta is equivalent to 126.444348. So if we just run all of that code there, helps if I load the package, and that will then load test that. If I run that, it's
Yay.
run. It gives us test pass. It gives like a nice little flare there. Hey, look at that. Isn't that wonderful? But importantly, if I try to call pop var here in my session, it doesn't exist. It only exists inside of this code here. If I were to run this code manually, then of course pop var would exist in my global environment. But the idea is that every single test is independent and it lives in its own little world.
Okay,
So
pause.
yes,
Expect equal. So
yes.
right now we've got, let's say for the alpha parameter, we have 6 significant digits to the right of the decimal point. That seems like a lot. We probably don't believe we have that precision. If we were to change this to 43.5, what happens?
Well, let's do that. Let's reduce both of these down to
Yeah.
those values. If we run that, it'll throw an error. And that's
Okay.
because of a thing called tolerancing. So basically it's actually going it's testing equality. It's using the equals function inside of R, which does have a tolerancing for it. So yeah, in this situation, we may not actually have that tolerance, but we can toggle that tolerance for us. And let's go through that in the next episode. It's almost like you knew what we were talking about.
Oh, well, I just took a guess.
Patrick, do you want to take us through this second example here, which does talk about tolerancing?
Yeah, sure. So uh, same rules apply. We're going to test that rederiving beta mu and beta standard deviation works, right? And so we're going to grab our population parameters, which we had from above. We know that those are the population parameters that our function above spits out. We know those are the true values. So what we're going to do here is we're going to say expect equals. We're going to use that beta mu function, and we're going to say expect equals. Take that function, give it the alpha and beta parameters. It should give us the average MLB batting average that we calculated, which is right around 0.256. And what we talked about before is that because we're using the expect equal and it's using R's built-in equality argument or function, we want to make sure that the tolerance is something that makes sense to us. So let's say, for example, batting average is generally often reported to 3 significant digits. So it'd be 0.256, really. We could set this tolerance to say like, hey, we don't really care about any of the leading values past those 3 significant digits, right? And we could set the tolerance just like that. Similarly, that function spits out a, a beta standard deviation, which we also take the alpha and the beta parameters from above. We use the beta standard deviation function. We take the square root of this, of the square root of the variance, and that's going to give us a standard deviation. And again, we give a tolerance level here. So here we're out to 1, 2, 3, 6 significant digits, it looks like. So we're expecting equals to be out to those significant digits now. So we don't care about anything else that happens after that. So if we run this, see what happens. And we get a little celebration, and you can see the emoji change. Sometimes it's a little party, it's a medal, a
Yeah.
rainbow.
It's fun. Feel happy about it. Your test passed.
Yeah,
That's a
yeah,
good thing.
so that's a little bit on tolerance.
Yeah. But those aren't the only things. So far, we've only done expect equal, but there are many different expectations that you can use. And in fact, oftentimes I find that the type of test that I want to be doing is really hard to do an equals with because it's a complex object. I'm testing a variety of different things, and so I want to create my own test essentially, and I'll have it return true or false, and then I just want to know whether the results are true or false. I don't want it to try to think and figure out anything for us. And that's where the expect underscore true function comes in. It only takes one argument and then it tests, is that value true or not? It's a lot simpler, but it gives you as the programmer much more flexibility in writing out here's what my expectation is. And the only requirement is that your expectation must return true for the expect true to evaluate. And so here again, we have our population beta parameters as a list in alpha and beta. And we're going to set up two types of scenarios. First, the number of successes or we're going to say n success LT pop average. So less than pop average is 10, and n success greater than pop average is 80, and the n attempts is 100. So we're saying one person tried, or two people tried 100 times. One person only had 10 successes. The other person had 80 successes. Right? So those are kind of the scenarios that we're developing right now. Once we throw them into our posterior beta mu function and we pass the population alpha and beta, the n attempts, which would be 100, and the successes. If that person has less than the population average, we would expect for the posterior beta mu function to return a value less than the population average, right? I guess we could also add in a quick double check to make sure that it is, though, greater than the something, because it's going to be somewhere between the population, because the population average, as well as where they're at, what their average results are. So we can test the two of these conditions. So first, checking to see, are you less than the population average, but are you actually greater than your individual average? Because we only seen 100 attempts from you. Similarly, we're going to test in this scenario, is it greater than the population average if if your current success rate is 80%. That is significantly higher than the average batter in the MLB 0.256. So we would expect posterior beta mu to return a value greater than the population average. So we can run this real quick. Yay, it passed. But if I had mixed that up here, let's show you. We've shown you a lot of successes. What if we did that where, oh no, I mixed my greater than or equal to sign. If you run that, it will fail. It'll tell you that you failed, and it's go, hey, I was expecting a true and I got a false, and it kind of tells you where it failed. It's a little bit difficult because here we ran this interactively, so it's line 18, but that's line 18 within this test here.
Yeah.
And so we can flip that around, run that, and it passes.
Yay.
Yay. Would you look at that? But the tough thing with this is we didn't write these tests to be very informative. It just says, yeah, it returned a value greater than 0.256. Not, this is the value that I was expecting. And so when you're writing your tests, you're going to want to do a combination of both very specific tests to tell you, yes, I'm getting this exact value, as well as other tests that are, maybe it's a little bit more difficult to test for, are you getting this exact value? So you want to test, is it giving me values in a reasonable range? Then a next sort of test. So these tests have been on specific functions, verifying that given these inputs, we're going to get a specific output. But another way you could do this is a regression test. And the only reason we're doing a regression test is we've already tested several of the functions explicitly, which allows us to go, well, now we want to make sure that all the tests or all the functions work together the way we'd want them to. And that's a regression test. So this code is actually just the code that we've gone through many times now during this series, taking the Llama data set, getting the population variance and average, getting the beta parameters for that population, taking a subset of that batting 2010 data set, and calculating posterior beta mu and SD. But we're introducing this new idea of a snapshot. So a snapshot doesn't have a value until you run all these tests once. Then it's going to record that value that you are saying I'm expecting. And now forevermore, it will be comparing against the value that you got that first time you ran this code. And so this is really nice. This situation's a little pedantic, but it's really helpful when you want to be capturing errors that are really complicated, messages. So if your code is returning a lot of messages that you want to record and make sure are consistent, snapshot testing is really useful for. So we're skipping over that. And then the final type of test that you might want to be running is verifying that it's going to throw an error when you put incorrect values in, or it's out of the bounds of your expectation. So now we're going to test that. Get beta parameters throws errors when non-numeric values are entered. And there's a few ways that you can do that. Patrick, do you want to take us through this?
Yeah, so this first one, test generically for an error. So expect error, get beta parameters is the function that we're running. We give it the population average as the test, and then we're checking that the population variance is the value. So if we run this, what I actually
So
what is popular? What is value?
so
This
what we're testing here is that this throws an error if we pass non-numeric values in there. But it's just testing that it threw an error. It's very broad.
yeah,
So test and value have no actual values, right? They're numeric or they're character values.
they're just just you could put anything in there.
Yeah.
Banana.
So we're testing to make sure that get beta parameters is going to go, hey man, you gave me a non-numeric value. I
This
can't do
doesn't work.
anything with that.
Yeah.
But it's a generic error.
Yeah, and then down here, it's the same type of thing, and then you have expect error. So you pass the get beta parameters in, and then on the right side of the comma, you have is numeric, population average is not true.
Mm. And in this situation, we are testing that it's giving this specific error. And so this is useful if you know exactly what your error is going to be and it's never going to be changing. This is the way you can write it. So that way you know
Get that
if
out,
you
yeah.
change your errors in get beta parameters to throw something else, this test will now fail because this is so specific.
Right.
Um, but you can also use regular expressions because actually this expect error is using I think a grepl under the hood. And so you can also write this more generically. So it uses regex or regular expressions, which we've done a series on in the past. You should watch that if this confuses you. Um, but essentially, what we're
Probably do
doing
a million
here,
series on regex.
so essentially, what this is doing here is it's looking to see if the error thrown by this function matches this sort of pattern. And this is what allows us to use the same sort of error message check, but change which of the parameters that we're entering is the one that throws an error. In this situation, it's going to be population average. We're checking to see if that is non-numeric, and if it's not numeric, it throws an error. Or population variance. If that is not numeric, it will also throw an error. But this is a quick way to do that.
Right.
So now that we've got all these tests written, we can go and we can do some fun things. So first thing we can do is I'm going to drag us towards the middle here. And if we run DevTools test, I guess I didn't need to drag us over there. We can put it here. It's going to run all the tests included in my package and verify that they all pass. And so this is a very quick way as you're developing, and you should be running tests fairly regularly as you're developing. This can verify that all your tests are continuing to pass, that the behavior that you're working with and are expecting has not changed, which is real nice. But on top of that, now that we know all our tests can pass, we'll need to quickly restart our R session, and then call DevTools test coverage. And what that's going to do is going to test to see what lines of code that we have in our R package have been tested. And so now we get this nice report out on the right here. I
A
don't know
little
why
shit.
it's saying restarting R still. We've already done that clearly. Clearly it's working. But we get this message here. So TidyX base coverage. We have a 56.67 test coverage percentage, which means 56.67% of the lines of code we wrote in this package have been tested at least once. We can see that the beta dists.r script, which is our beta distributions R script, has 100% coverage because those are the only tests that we wrote in this example. And then our gamma dists are not covered at all because we didn't write any tests for them. You can click on that and that'll bring up a report showing exactly which lines of codes had been hit. Conversely, if oftentimes it's not as clear cut where one file is tested, one is not, but you can go into gamma dists and you can see which lines of code have not been tested yet, which allows you to then write better tests or write more tests to try to hit those lines of code. And the goal, generally speaking, is to get as high of a test coverage as possible, as close to 100% as you can. It's not realistic to expect 100%. 80% is good, 90% is fantastic, 95% even better. But don't take, if a package doesn't have that high of a test coverage, that's okay. That's not
How
the
much do you
worst thing.
need to get accepted on CRAN?
There's no requirement.
Oh, really?
Yes. The
I
only
thought that would have
requirement
been.
from CRAN is that all your tests must pass. So you can choose to not include tests in the code that you send to CRAN, and that's okay. They will still run your examples, so all your examples must still pass. But you don't need to have tests inside of your R package in order to submit to CRAN. That's the common misconception.
Yeah. Interesting.
And then the
Okay.
last thing that you can do is run DevTools check. And what DevTools check is going to do, it's going to verify, it's going to redocument your package, rerun all your examples, run your vignettes, and run a series of checks to make sure that somebody else could install this package on their system and have it basically run. And it'll check a variety of other things. So this is kind of a, hey, before you send it to CRAN, you need to do this, and there's a lot of requirements before you send, or things you need to do before you send it to CRAN. But let's not worry about that right now. So this is just going through and verifying that somebody else can use this. In this situation, we have some potential errors. For example, we don't have mutate imported into our R code. That's okay because we're not planning on distributing it for anybody. But generally, there's no warnings, so I'm generally pretty happy with this function, and I think that any of you watching this could install this R package from our GitHub page and use it if you want. And so with that, that is a very high level discussion and some examples of how testing works in your R package in R. With that, I think we can cut it right here. Right, Patrick?
Yeah.
All right. As always, my name's Ellis Hughes. You can find me on various social media sites at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter or X at at OSP Patrick. You can find the screencast on X at tidy_explained, tidy.explained@gmail.com is where you can hit us up with a email. But liking and subscribing on the YouTube channel is the fastest/easiest way to get in touch with us. So leave your questions, comments there. Other than that, we do have a Patreon page, and if you feel like we've been helpful in your work and our progress, and you'd like to donate to the show, the Patreon page is where you can do that, and we're very appreciative of all that have done that. And with that said, that's
Thank you
episode
all
159.
so much and keep on exploring your world.